Hey Juan, how are you doing? Good to see you.
Excellent.
We'll get going in just one more minute, folks. All right, John, I'm going to go ahead and get going here. So my name is Trent Jacobs. I am the digital editor at the Journal of Petroleum Technology. And it's my pleasure today to be a moderator of this excellent panel. I think everybody that's joining in is going to get a lot of value out of it. Real quickly, without any more fanfare about myself, I'm going to introduce Rebecca Shipman, who is the president and CEO of Reservoir Data Systems, and she's one of the people that has made the panel discussion today possible. Rebecca, can you hear me? Are you there?
I am here. Can everybody hear me? Yep. Wonderful. Good morning, everyone. As Trent said, I'm Rebecca Shipman. I'm the president of Reservoir Data Systems, and we've teamed up with Saga Wisdom to put on this webinar for you, and it came together very quickly. John Thompson and I had a conversation just last Monday, and we both agreed that we wanted to get some valuable content out to the industry as operators were navigating how to shut in production and folks were already beginning to shut in wells. We both firmly believe in the value of this data, and we have seen how savvy engineers and operators have utilized this to give themselves a competitive advantage. And we wanted to get this message out to the industry as we're all kind of navigating these unprecedented times. But this morning, I actually want to pose a question: is the oil and gas industry actually in an unprecedented time? As you all may know, our industry has a rich and long history. There are countless stories of challenges and upheavals, plot twists, all of which were met and overcome using science, innovation, and resourceful problem solving. If we rewind just a little bit over 100 years ago, we find ourselves at a very similar intersection of the Great Depression and an oversupply from the oil boom from the development of some famous fields. Consequently, oil price collapsed and at one point got to about 10 cents per barrel, which is roughly about $1.43 in today's money. Well, this led to a whole host of government interventions and pro-rationing of oil in efforts to slow production. But producers back then aren't like what they are today. They were a bit more aggressive and rebellious and less refined, and they refused to comply with those pro-rationing efforts. So then governments had to come in and they actually implemented martial law to force producers to shut in their wells. So I would argue that what we're experiencing today with demand destruction, oversupply, and economic peril is not entirely an unprecedented situation. Our industry has been here before. But I think we can all agree that our situation today is slightly more complicated and a little bit larger global scale than it was over 100 years ago. So while there's no exact precedent for these challenges, we can choose to be smarter today than we were 100 years ago. And we can choose to be smarter tomorrow than we are today and give ourselves as an industry the best chance of success on the other side of this. While shutting in production is a trend that's being manifested under duress, it is a once-in-a-lifetime opportunity to acquire valuable shut-in and build-up data. Never since the advent of multi-stage fractured wells have we had the opportunity to study and characterize unconventional reservoirs like we do today, to learn valuable insights beyond just reservoir pressure, things like frac conductivity or near wellbore effects, damage, well interference, just to name a few. And you can use this information to save significant dollars for efforts like well spacing optimization or infill drilling on your completions designs, preventing damage, or knowing how to stage your wells back online. Overall, improving returns from your reservoirs. So in a sense, we are putting our wells into quarantine. And as we're doing that, let's take this time to learn more about them and get smarter in the process. So without further ado, I'm going to turn it back over to my friend Trent Jacobs so he can get started with our panel. We hope that you find a lot of value in this content and that it will help you make decisions going forward. Thank you.
Thanks so much, Rebecca, for that introduction, and thank you to Reservoir Data Systems. Real quick, I'm just going to share my screen, and we're going to do just a real quick housekeeping kind of checklist, so you can see right here who's going to be speaking today. Down on the menu area, you're going to see some of you have already found it, a place where you can ask questions to us, send text, and we want this to be an interactive experience. So if you have questions as people are speaking, bring them up. If you have a question for a specific speaker, go ahead and tag that speaker so that we know who you're trying to ask the question to. We're also going to have some poll questions. So this is another one of the little deliverables that you will get today. You're going to get a sense of where everybody in the audience is today with the shut-in issue. But that is it. So I'm going to keep that very brief. We'll pop up the agenda a couple times throughout this to know where we are. Our first speaker, though, is going to be Dwayne Purvis, and he is a petroleum engineering consultant, and he's going to talk about the overview and the value proposition of monitoring these shut-in wells. Dwayne, are you with us?
I am indeed.
Okay, the show is yours. Take over.
All right. Hey, thanks so much, Trent. Good morning, everyone. My name is Dwayne Purvis. I'm going to share my screen now, and we'll start with the basics, the bottom line starting point. Chairman of GE was famous for saying once, "We're not in the business of making cars; we're in the business of making money." And by corollary, we are not in the business of making oil; we're in the business of making money. The problem is we don't actually make money directly. What we make are decisions and holes in the ground. And we hope that those make money. The quality of our decisions determines whether or not we make money. And that's the end result of our process. Decisions, though, are predicated on analysis, and analysis is predicated on data. Data is our raw material. Chemical engineering or civil engineering, they maybe get to start with some governing physics and a blank sheet of paper. We're constantly trying to reverse engineer what has happened, what exists, so that we can manipulate it. And data is how we understand. Now, when we go to drill a well, we spend a ton of money, and we get a sort of blurry picture of what we have constructed. Now, I worked for an operator whose annual drill program wasn't particularly large, but it was large enough that if he'd spent the same money to build a building, he would have changed the skyline of Fort Worth and had a marquee property that will be known for decades. We spend enormous sums of money and sometimes get calloused to how much money we're actually spending. Our early time data doesn't give us a great deal of information, and there's a good deal of uncertainty when we're just looking at decline curve analysis. There's a great deal of uncertainty about what recovery will be. The early physics are not the same as the late time physics, and it's the mid to late time physics that control ultimate recovery. The range of uncertainty, early time, decline curve analysis, unconstrained, without good processes, is a very wide range. So over time, we narrow that down. We get a little bit better picture of this thing that we've built. I was talking to Dr. Tom Blassingame once about using public data to do an analysis, public and decline curve analysis, because that's all I could do. And his comment was, well, if you're doing analysis on public data with decline curve analysis, he says, well, you're going to get what you deserve. Characteristically snarky. Over time, we do eventually narrow it down, but of course, it takes a good deal of time on the scale of years to start to see from the data, from the production data alone, what the longer term trends are going to be. But there is a way to constrain that, and that's rate transient analysis. This is probably the most underused, the highest value compared to easiest data and analysis techniques, the most underutilized tool, I think, in the engineer's toolbox right now. This adds an additional constraint. You see a graph like this. Dave Anderson will talk about this graph in particular, but it's only one of a number of kinds of analyses we can do under this umbrella of rate transient analysis. But when we bake in the pressure data as well as the production data, we add constraint and we accelerate the insight. We're able to get a clearer picture much sooner in time than we would with production data alone. Now, that's not the end. RTA is a great gain, huge process the industry has gone through, huge learning curve to make it into a really viable, valuable, if still it has some limitations, viable and valuable tool. But it's not the only tool we have. And when we go to use another kind of analysis technique, we get a slightly different perspective. And that's what pressure transient offers in this situation, or long-term pressure monitoring. It's a slightly different perspective on the same thing that we've spent a boatload of money to build so that we can understand. You're used to seeing graphs like this, and this is an example of something that Dylan will tell us more about. The points here are, by way of introduction, are just a couple. First, we've got logarithmic time here, right? And the first response in the time period, the first responses that we get, the responses in this time frame, are measured in seconds, and that they pertain to the part of the system closest to the wellbore. As time progresses and the pressure wave moves out, the response that we get is governed by the area that it has moved to. So in the middle time, we get to see bulk reservoir properties better. Late time, we get to see the farther extent. We don't, these time references in days are for reference for this particular example, not generic. The lower the permeability, the longer it takes. And the farther you get out, the longer it takes to get data. So because it's a square root function, to double the investigation distance, you have to quadruple the time. So usually when we interpret pressure transient analysis, we're doing stuff that's in this time frame. But we have the opportunity now to see information that's later, that's farther out in the future. And this is another example of a really long-term forecast that Dylan will unpack for us again some more. 210 days. And in this case, he was able to extract some really valuable information from this very late time. And even if we cut off the early time period, we still have some opportunity. And of course, if we go put a pressure measurement gauge on a well as we bring on an offset, we also have the opportunity to look at interference. So there's value to be had from mid to late time buildups also, although it has risks, which others will talk about, but there are ways to tie it together. So what we get with the combination of rate transient and pressure transient is a combination view. We get two perspectives on the same thing that we've created, and therefore we get a better, more complete view, and we can make better decisions. So with two perspectives, we have more information, we have a more unique interpretation, we have more confidence. what's going to happen here in the near future is we're going to start bringing these wells back online, and the wells are not going to just pick right back up. They're going to, maybe they will, they're going to come back a little higher, a little lower, or on some kind of, and certainly with some kinds of transients. And our analysis of reserves is actually going to be set back. If we're only relying on decline curve analysis, our understanding and our reserve estimates are going to be set back. But and during this time, when we're doing nothing, our understanding is not growing. At least our understanding from pressure and production data is not growing. But we are going to face challenges in the future. And the more we have, the better use we make of what's going on right now, the better we will be able to address those challenges. I understand that the data is, in some cases, what we're going to acquire is going to be limited. It'll have constraints. The good news is that there is a way to tie it all together. And this is a terrible graphic, but simulation. It would be a terrible simulation grid, but others will talk about how we can use simulation to tie it all together to come to one unified, well-constrained, even if it's not perfectly unique. It's much better constrained than decline curve analysis, or better constrained than one analysis by itself. Now, so we don't have to do everything quite idealized to still get good value out of it. But then that data, that analysis becomes reusable. So the next time we build a building that we spend $5 or $10 million, we can bring to bear the analysis we've learned from other places, and we're better educated to make those decisions. One of my personal favorites is to use RTA and simulation to make a forecast, bring it into PhD Win, curve fit the history match, curve fit the forecast, and use those to use that as a guide to the decline curve parameters I'm going to use in the future. We are able to get new information, better information, during this time period that's useful not just for our existing wells, but also for future wells. Now, I have been accused of being just an engineer, and engineers always want more data. That's true, but it's incomplete. My brother is a marksman. For fun, he likes to shoot at metal plates at 700 and 1,000 yards. And he really loves his optics, his binoculars. He'll pull out a Zeiss or a Swarovski lens and say, man, look at this. Isn't it gorgeous? Such a great view. It's clear, sharp, bright, big. And I kind of dismissed him too, but until he explained it to me. The rule of thumb among marksmen is to spend at least as much on the scope as you do on the rifle itself. That's the rifle that does the shooting. It's the rifle that does the hitting. It's the rifle that actually gets stuff done, but the scope makes it possible. You don't know what you're doing. You cannot take good action without a good scope. And that's what data is. That's what analysis is. It makes it possible to make good decisions. Now, to be perfectly fair, our industry is not like a sniper rifle where we can hit a 4-inch plate at 700 yards. It's much more like a musket. You're gonna, you're gonna miss. You just don't know how much. Now, when we had the last bust 5 years ago, we played out almost completely played out two of the three strategies that we have. We've made some progress on analysis. We played out the strategy of cost reductions. We squeezed our suppliers so hard they started going out of business. There's no more blood in that turnip. We squeezed the geology. We high-graded our acreage systematically over years. We can't high-grade anymore. There's still some locations there. But we squeezed those two. We did improve our analysis some, but that is the knob that we have left for this for this downturn. So I always remember a line from The Patriot. They're shooting the movie. They're shooting muskets, which are notoriously inaccurate, but their lives depend on taking good shots. And the wisdom from the dad to the young shooter is aim small, miss small. We know we're going to miss. We're shooting muskets. But data makes it possible for us to aim small and succeed in the shots that we're taking. That's what I got. Trent?
Hey, Dwayne, thank you. That was great. Especially love the history lesson there. That put a smile on my face. So I'm going to jump right into one of the questions that we got from the attendees for you. One of the drawbacks of RTA is being relatively more time consuming and data demanding compared to DCA. For example, stepping into a new area with 100+ wells, how is it possible to do RTA for all those wells before coming to a conclusion about the reservoir?
It's a good question. It does take longer, but it's kind of a false alternative. It's not all DCA or all RTA. Now, if the shut-in goes in long enough, maybe you have enough time to do all of them. RTA, once you're experienced at it, will take on the order of hours for a single well. When I've done this in the past, what I've done is to select a small number of the total wells, depending on the project, some manageable number. Analyze those with RTA, use those conclusions to guide my DCA. So I want to make sure that I pick wells that are representative. They have representative fluids, and something with enough history that's well enough behaved. I analyze those. As I said before, I take it into PhD, curve fit it, get a better feel for the range of decline curve parameters that accurately reflect that that grouping of properties, and use that for the rest of the wells where I'm only going to use decline curves.
Yeah, so do yourself a favor and sort of try to triage the amount of homework based on what you hope to get out of the data.
Well, I hate to tailor it too much, but you want to choose a small set that's representative, something from which you can draw lessons.
One thing we had talked about earlier between you and I was sort of, this kind of ties into this question, how do companies, subsurface engineering teams calculate the value of this information? What's the ROI here?
Yeah, no, I really wish that were a subject of physics and derivations, right? But it's not. It's not something we can calculate in a hard and fast way. What we get out of data depends, one, on how much we have, two, on how we use it, but also there's this large scale uncertainty, this stochastic kind of, sometimes you get more, sometimes you get less. But all the decisions are built on data. If we have, and the decisions we're making are really, really big. There was a time not very long ago, less than 15 years ago, where the average gas well in the state of Texas cost $600,000 to B and C. Today, you're hard pressed to rent the Porta Johns for $600K. When I have the opportunity to get some data for free, the ROI is infinite. It blows my mind when people are not chronically testing, when they're not always having something in test, when they're not always getting good flowing pressures or shut-in pressures from the wellhead. That's no cost, and the ROI is infinite because its cost is zero. Now, a lot of the ways that we get data, cores and logs and microseismic, are really, really expensive. And there's a certain amount of critical mass that may be necessary to reach an understanding then that extrapolates to your whole portfolio and all your work. But in the scale of data gathering, the gauge work is really on the cheap end. And it doesn't take much return, much gain, much change in design, much incremental production to pay out in multiples. So, to my way of thinking, and right now we have no other alternatives on how to, we have time to improve our analysis. We have the need to improve our understanding. And this is cost effective. It seems to me that it's a no-brainer. The ROI is there.
Well, Dwayne, at the risk of going over just a little bit, I'm going to give you like 60 seconds to answer one more question from the audience here. And this one comes from Hamed Bazadi. How to constrain last impacting parameters such as endpoint permeability? Can you answer that one in 60 seconds?
I wish I could. I apologize, Ahmed. I'm not sure I understand the question. I will say this. We get different kinds of, we see different kinds of things with different kinds of analyses. And what we want to do is make an interpretation that fits all of it. And so if we have a couple of kinds, we can look at it different ways. And sometimes we may need to bring something else from another location. One of my old favorites was to take old vertical wells and simulate those to try to determine matrix permeability and then use that as an input to simulation in the future. It doesn't have to be self-contained to a single analysis.
Okay. Well, Dwayne, thanks so much for your presentation. And we saw some questions about your slides being available. I think that we can do that. You're going to stick around for the general Q&A at the end. So thank you, Dwayne, and we will keep moving right along.
My pleasure. Thanks, Trent.
Thank you. Up next, we were going to have David Jones at Chesapeake join us, but unfortunately, he wasn't able to make it today due to some prior commitments. So instead of David Jones, one operator, we have two operators today. So I want to introduce our operator dialogue session, Nathan McMahon and Trevor Engel. Nathan is a staff reservoir engineer with ConocoPhillips, where he has worked for 13 years. And Trevor is a senior completions engineer at Devon Energy, where he's worked for the past 9 years. Thank you, gentlemen, for joining us.
Morning, Trent. It's good to be here.
Yeah, good morning. Thanks for having me.
Yeah, well, I wanted to start with you, Nathan. And, one of the things that we were going to talk about with David Jones was about, candidate selection. And when we were talking, some of the things that came up were some of the concerns that you should have when you start shutting in well, when you look at these candidates. So can you take that one on?
Yeah, so certainly there's a lot of chatter going on right now about shut-in and loss of productivity and how much is going to come back. As operators, we shut in wells all the time, with offset fracs and workovers and those types of things. And I think the key question here is, what might be different if we shut in for some extended period of time beyond what we normally do? And so immediately there's concerns about well integrity issues. Are we going to have some more failures with wells? But we can remediate those. And then quickly, reservoir engineers go into the subsurface, and are we going to have issues with water block or fractures collapsing, or other issues with emulsion and paraffins and things that might plug up the productivity of our reservoirs? And that's a little bit to be seen. And there'll be some simple techniques we can do. But I think the bigger one is a lot of these low rate wells that are out there. How are we going to be able to bring them back, and will they come back at all? And that'll be low priority probably for the operators. They're going to bring on some of their best wells in those wells that easily come back. And then as prices improve, they'll be able to go back to those and work through. And I try to spin it to where we can see some positives here. I think one thing you'll be able to do is you'll be able to identify some good, maybe workover candidates. You'll get some of this pressure data where maybe there's more productivity there than you actually thought, that you will be able to take time and actually go work over and improve some wells because you have this data that you didn't have before.
Right. And, Trevor, I wanted to bring you in because you had watched the video that's on the Saga Wisdom YouTube channel that David had put together. So for everybody out there, there's a supplementary video that you can go watch. It's about 2 minutes long. And you had some takeaways from what David Jones at Chesapeake was saying. Did you want to, go over a couple of those?
Yeah, I think that's a great idea, Trent. For those of you who may have not gotten out there to watch the video yet, I'd highly recommend it. I think David did an incredible job of providing an operator's perspective of the things we're thinking through when considering candidates for shut-ins. I'd like to just touch on a couple of those key points for you. I have to say first, across the industry, across the US and internationally, we're all probably dealing with different constraints that we do or don't have within our operating areas. Some of us maybe are impacted by downstream storage capacity issues and purchasers not physically able to move our barrels while others may not have experienced that yet. And I think David did a great job of hitting on that those constraints are really going to set up what the goal is or the objective for each company during this unprecedented time. And I think that in particular, the goal of each company is probably going to set the magnitude and the scope of how impactful the shut-in is for each operator. While some of the operators who maybe don't have constraints downstream, they may be less impacted by shut-ins. However, we're all still suffering to some degree on the revenue side by the low oil prices and have wells that have become marginal because the revenues aren't outweighing the cost it takes to operate. So we're all impacted in some ways, and that in general is going to guide the scope and magnitude and the company's goals. Beyond that, I think he touched on a lot of considerations that each of the stakeholders in the organizations have. A couple examples he brought up that I share a lot of sentiment with are some of the land and legal considerations around, are these wells that we may need to shut in leaseholders? You obviously have to consider what the impacts and value loss would be. And I'd say some other examples he brought up are these subsurface teams are going to have to dive into the data, understand where around their fields, what different reservoirs may be impacted more or less by these shut-in events from a damage mechanism standpoint. But at the end of the day, I think it's these practical constraints and considerations that he pointed out that will ultimately drive the well selection criteria, not necessarily the data collection. That said, as Rebecca mentioned earlier, this is a perfect time to be opportunistic, to capture data that we know can help us characterize our reservoirs, our fracture geometries, our landing zones. I think David did a great job of spelling out a couple of those options through RTA, PTA, which I know will be covered even further in this webinar, and also interference testing, which is on the session for next Friday. And so I think David's video is great, and those would be some of my key points.
Yeah, thanks for that. Nathan, I want to switch back to you real quick. This is sort of a big question, and I think it's going to be covered here a little bit later too, but can we even get useful data using surface gauges? And somebody else asked us, do we have to use downhole gauges? What are your thoughts there?
I mean, certainly downhole would probably be preferred, but right now we're in a very reactive mode, and frankly, it's hard to react quick enough as things continue to change. And with everything going on, to have those things in place, it might be hard to have the ideal situation. So, maybe you would go to where you already have those gauges and you have the opportunity to learn and prioritizing those wells that shut in. But in terms of using the opportunity, I think we have to be a little bit practical. It's not ideal in terms of the data acquisition, and we might not be able to do as robust a technical analysis through well test type things, but I think there'll be other things we're able to extract from it. So if you can use the opportunity to collect a higher level of data, work with your field folks to gather some observations, dust off the echometer equipment and do some fluid level testing through time. And I think we'll be able to synthesize things we're not imagining that's beyond just specific technical work. So if I go back to my example in the last question, identifying remedial candidates. Some people are looking at refracking early generation wells, and will that help you prioritize which ones might be the best ones to go after, because you're getting some of this data that tells you there's probably a little bit more energy left here and resource left in that place, that you'll prioritize some of those opportunities. So it won't be the most ideal technical solution that Dave can talk to a little bit, that in terms of the technical analysis, or Dylan, but we'll be able to extract something from it. But one thing I would focus on is, Dwayne's talking about narrowing the uncertainty range with the improved technical analysis, but sometimes that's not quite enough. So if you're going to take time to collect this and analyze it, be a little bit more purposeful about it. So what might you do differently from that? And I like to focus on, what decision would you change? So if you go back to some of the pilots you've done, how can you use this to enhance where you've already invested money, and you're looking at those different opportunities of how to change the completion, the well spacing, stacking, or sequencing, that you'll actually do something different coming out of this. And that's kind of where we need to focus technical folks to think of that and seize the opportunity right now.
I got a question from Steve Hudson that I'm going to put to both of you guys. So whoever wants to take the first swing, please go ahead. And the presenter's experience, is there an amount of time for a well to be shut in that they see any diminished recoveries or damage to the productivity, both in gas and oil reservoirs? So this is working a little bit on the assumption that these wells will bounce back because we've had to shut them in for infill operations. But if we're talking 2, 3, or more months, what does that do?
Yeah, so I'll jump in then here, Trent. But we've had to shut in wells for an extended period of time, a couple months with workovers and just a backlog of workovers or weather events that happen. And so in that time period, haven't really observed too many things in my experience where they don't come back well. Although you do have the occasional poor well where something goes wrong and you can't recover from. So it's really, in my mind, getting into that. If you're going to be shut in for, say, more than 6 months, that we're going to start to have concerns. And then I also think about how different operators are going to have different philosophies, and are you going to have some competitive drainage issues, those things you're going to want to monitor for that might change the priority of which wells you're shutting in and which ones you keep flowing to maintain your leases and those types of things. So there's some additional surveillance there that you're going to want to watch for.
I'll add one thing. I'm not the expert on this topic, but one of the things that's come up in some of the discussions here at Devon as it relates to extended shut-ins and how they'll come back is the presence or absence of H2S. In some fields, some reservoirs have H2S, and that's something that our production engineers have been thoughtful about, shutting in those wells with H2S, any type of separation and potential corrosion that could happen to the due to higher concentrations in parts of the wellbore. So like I said, not the expert, but I know it is being considered and maybe something for those in the audience to think about.
Let me just piggyback with you, Dathan, on this one for one more second. These troublesome candidates or these trouble wells, should you have some, do they come as a surprise, or do you have a pretty good idea of what to expect?
Well, I think if you look through history and you look at the wells in your field, usually the better wells are going to come back stronger and they're going to do well. The poor wells, you're not going to see as much response from. And so that's where I take advantage of the idea of, does that tell you something about that well? And you learn something about what makes one well better than another. So that's kind of the way I view it, at least.
All right, I got another question from the audience. So this comes from Mary Van Domelin, who's a distinguished lecturer. What historic data from the execution of the completion, e.g. frac jobs, would be most useful to integrate with your analysis of the shut-in well behavior? So what historical data should you go pull out of the files?
I had a stab, Nathan, and then maybe you could build on it. But I think on the frac side, the industry's come very far very quickly as it relates to offset pressure monitoring. I think there are several techniques out there that give us the ability to understand and see fracture arrivals, be able to describe and understand the fracture geometries, the distribution of those along the lateral, and maybe how that even changes from completion design to completion design or different stage architectures. I know within Devon, we focus on a new technology that has been developed in-house by Kyle Hosfite and others called sealed wellbore pressure monitoring. And we feel like with it, we learn a lot about completion efficiencies and uniformity of our fractures, but also the fracture geometry that can ultimately be tied to further help constrain a pressure transient analysis or a buildup like Dwayne mentioned earlier, getting data from multiple sources to help constrain the likely outcomes.
Yeah, just a little different perspective.
Nathan, did you ever thought to add?
Yeah, if I can add to, like, if you look at history, one of the things I think we need to consider beyond looking at the completion data, like Trent or Trevor talked about, is do we have prior shut-ins we can compare to, and how have things changed with time in terms of fracture conductivity or even connection between wells if we look at interference and communication. And someone made a good comment earlier about being able to take advantage of frac hits and what we see here and study that conductivity. Does it remain? Does it go away? So I think there's several different things to extract beyond just looking at the completion data when we look back at the history.
Good points. Yeah, and the sealed wellbore pressure monitoring, we've covered that in JPT. So anybody that hasn't read that or heard about that paper yet, go check it out. It's one of the hottest topics we've seen in completions in many years. We had a clarification question come in from the audience, so maybe one of you guys could take this on. But and I think this may have came from Dwayne actually, but maybe you can take it. When people talk about fracture collapse, are we talking about proppant crushing or something more severe?
Yeah, I mean, some people worry about proppant embedment. If you're having fluids and things sit there, and if you have a softer rock and more clay, or is it give it the opportunity to collapse that fracture? And as you're having different geomechanical effects as that shut down. So those are things that could happen. There's a lot of talk on hammer effect, and if you shut in a well too quickly, what might happen there in terms of damaging fractures. Those are the types of things I think everybody's concerned about.
Nathan, I had one more for you. Can you just touch on what a best practice might look like if you're going to approach a shut-in with the idea of running a test? Are there some non-obvious tips and tricks there?
Yeah, from my experience, just to kind of try to get the best out of it, I pose that question, how can we be more purposeful to learn? So we're not always doing these types of buildups and collecting this type of data. So if we can just take a breath and pause and actually come up with a good design and procedure. And one of the best things that I found is taking time to get your MSOs and field staff into a room and talk through that procedure and just actually get a good idea and a good alignment on what you're trying to achieve, and explain to them what you want to get out of the test, and also to use their eyes out there, what they see and record, and get some good notes. So if you see something in the funny data later, oh, they actually moved this valve or did this, that might have done something different. So taking that time to go through that, to have a thoughtful design, to communicate with the folks, because they're running through priorities, right? And sometimes when you get that request there, they're just going to go run and accomplish it. But to actually have that common goal and them understand the value of the benefit, then they're going to higher prioritize the time that they take to implement that test for you.
I got another good question on this thread, and it's from Rick Stanley, and he's asking whether should operators be able to lean comfortably on their SCADA collection, using SCADA data for the pressure analysis, or do you actually have to go use a more purpose-built pressure sensor on the wellhead if you're going to run test? Oh, you're mute, Nathan.
I actually hit the mute. Thanks, Trent. So I think you can use it. It'll depend on your network capacity and how you can ramp up that data to collect it in the right manner to do it. So, and if you can't do that, then the easiest thing is to get a gauge where you want to do those tests and put on top to acquire that data. That's fairly inexpensive compared to some other methods. So I think it is possible, but you have to work with your SCADA folks, and depending on how many wells you're trying to connect it into and the frequency that you want to gather, and you have the right network set up to store and collect that data at the right frequency.
All right, well, thank you, Nathan and Trevor. We're just about out of time here, so we're going to keep it moving, but I want to remind everybody in the audience that we are going to save some time at the end, so that if you want to direct a question towards anybody, we will circle back to that. Okay, well, we're going to transition now to David Anderson, who's going to talk to us about the review of the fundamentals. David is the CEO of Saga Wisdom and a recognized expert in rate transient analysis. And if anybody is using Harmony out there, David is one of the original software developers when it was known as Fiquette. David, show's yours.
Thanks, Trent. I'm just going to try and share my screen here. So I'm going to talk about fundamentals of RTA, PTA this morning. And I think in order for us to understand as an industry kind of the unique opportunity we have right now in front of us that some of the other folks have alluded to, it's good to maybe take a 30,000-foot view of kind of where we came from. And I've spent almost my entire career working in the field of RTA, PTA as a consultant. So I've sort of seen how things have developed over the years. And I think it paints a picture that really tells a good story as to what we can do as things stand right now in this sort of unprecedented condition that the industry's in. So I'm going to do a little bit of fundamentals, a little bit of storytelling, and hopefully it'll be of some interest. I'm going to start with this idea of a well testing toolbox. And if you can think of a toolbox, and Dwayne used the building analogy, so I think this aligns quite nicely. Some of these tools, to be honest, are pretty dusty. They haven't been used, certainly in the onshore North American playground. You don't see these things coming out very often, but I think it's time to dust off some of these tools and start using them. I divide these into two categories, what you might call controlled tests. And controlled tests, I haven't named them all here, but I've named, I think, some of the more popular ones, multi-rate tests, pressure buildup tests. There's going to be a lot of talk today about pressure buildup tests because for reasons that you'll see in a few minutes. But then there's some of these other tests as well. Now, these are all children, if you want to call it, of the PTA, pressure transient theory, which is really based on the constant rate drawdown, which I'm going to get into in a minute. And then on the other side of things, so as a tool, I sort of look at this as a finely honed instrument, such as a scalpel. So these are tests that are designed to collect specific information to solve specific problems. And then on the other side of things, you have uncontrolled tests, which really, as Dwayne alluded to before, this is really just one thing. This is what we have available to us after the well goes online and on production, and that's all our production data. One of the advantages of the uncontrolled test or the RTA is, as Dwayne alluded to, is it's basically infinite ROI. I mean, this is data that we get for free. Essentially, as engineers, we can, we'd be fools not to use it and get something out of it. So as a result, there's a lot of work done with this data. I think of this data in as a complementary way as possible as a blunt instrument. It's not designed to give you high precision, high resolution answers. We are often dealing with a lot of uncertainty due to low resolution in the data. And because it's uncontrolled, we're dealing with lots of inputs that we don't understand and we don't have control over. So we become, as RTA practitioners, we have an extra layer of having to be data experts as well and understand how to filter data and get noise out of there and search for that reservoir signal. The analogy I like to use here, I find that reservoir engineers like using analogies. I haven't met one yet that doesn't use analogies, so I'm going to put one here. The controlled test is sort of like if you're in a room with, or if somebody's in a room with the TV blaring really loud and they're whispering, and you're on the other side of the room and the door is closed and you're trying to hear what they're saying. Okay, there's all this noise. Sorry, that's the uncontrolled test. So you're on the other side of the door. You can't hear, what they're saying. There's a signal in there somewhere, but you really got to search to find it. That's what we do with RTA a lot. That's my best analogy for it. The controlled test is I can open up that door, I can turn off that TV, and I can listen directly to what the whispering is. So I can see a lot closer, or hear, and I guess in this analogy, I can hear exactly what's going on. It's a much higher quality signal. I will point out also that some of these tests, controlled tests, we do have the option to conduct these inline, and some of them we don't. I mean, we can't do a drill stem test now. That time has passed. We're not drilling the well anymore. We can certainly do a multi-rate test or a pressure buildup test. This is important in this consideration because we have these wells sitting here. So let's collect some data. Let me talk a little bit about the constant rate drawdown. Most of you, I think, are more than familiar with this. I'm not going to belabor it too much, but this is the reason why I stress this point is because this is the equation that really all testing and all RTA is based on. Anything that we do that has to do with well performance-based characterization has its roots in this. This is the ancestor of all of it. So it's a really important thing to understand. So essentially we flow a well at a constant rate and we start measuring the pressures. And the left-hand plot shows what that looks like on a time basis. The right-hand plot shows what that looks like inside the reservoir, distribution of pressures inside the reservoir. Now, interestingly enough, as a practical test, the constant rate drawdown is not very practical, right? It's the equation that everything's based on, but when we actually test a well, we're going to use all this diffusivity equation, this pressure drawdown equation, but what we're actually going to do is going to apply it to a pressure buildup test instead. And again, go back to my analogy of trying to listen when the TV's blasting and somebody's whispering. What the pressure buildup does is allows me to open the door, get right inside and hear exactly what's being said. It's a much cleaner signal. And so conventionally, that's the way testing is done. And that's, in offshore environments and conventional environments, that's still how testing is done. We always use these buildups. It's a much cleaner signal. We can, get much higher resolution, much more of a noiseless interpretation of what's going on. So that's your pressure buildup. So when I started my career at Phuket in the late 1990s, every single well that was drilled in Alberta, there was a regulatory requirement that these wells had to have an initial flow and buildup test. So typically this is what it would look like. You'd run these things on a test separator, a flow and buildup like this, and then you'd put the well on production and you'd have your production after that. So we had to do all of our reservoir characterization here. And that included doing a production forecast. Now, as you can imagine, that wasn't the best way to do things because in a flow and buildup test done before we have any production, we haven't really seen much of the reservoir. Sure, we have a very, very finely tuned instrument that can measure in detail very closely what's going on, but we can't see very far into the reservoir. So we did this for many years, and it wasn't until later that the RTA techniques started to be developed, where we got a much better understanding and realized we could use the flowing rate and pressure data to get, to understand things, understand the total hydrocarbon system a little bit better. So if I look at sort of the relative popularity of PTA and RTA over the years, it very much coincides with the reduction in conventional plays being developed. And that reduction was not a choice, that reduction was by necessity. I'm sure there isn't an operator in the room that wouldn't go after conventional reservoirs all day long if they were still available, but these are in short supply. This was the low-hanging fruit. Most of it's gone now on the onshore North American environment. And so as a result, we wanted to keep producing oil and gas. So we went after started exploiting the lower permeability resource plays, the unconventional wells. And that's where RTA incidentally really started to take off. A couple of reasons for that, I think, are clear to most of you already, and I think Dwayne alluded to some of these. RTA provides key information that's not available from that initial flow and buildup test, namely the time component of it. So the ability to look at how things are evolving over time, the total hydrocarbon system, seeing that total drainage volume. But I think it is equally important as that, it became prohibitive in terms of the economics to shut in these wells, right? So when you're trying to do these initial flow and buildup tests on wells that are microdarcy and nanodarcy, it's not really practical. In fact, sometimes you can't even flow the well. So you would instead maybe conduct a flow and buildup test after the stimulation treatment was done. And all you're seeing in that test is linear flow. So you're really not getting anything useful out of it. And nobody wants to shut their well in for 2 or 3 years to get that prerequisite shut in or build up data. So RTA became really the tool for characterization. And the current situation that we find ourselves in now is we have, as an industry, a wealth of RTA interpretation out there. I mean, everybody's doing production analysis. 15 years ago, really, it was all decline curves. Now there's a lot more RTA going on. We have a pretty good understanding of the accessible hydrocarbon pore volume and recovery, and a pretty good understanding of what I would call the bulk or blended reservoir properties. Because RTA is a blunt instrument, it's not allowing you to see in detail what's going on, near the wellbore. It's sort of amorphizing everything together, homogenizing everything together as a blended, we talk about A root K, and we talk about, some of these bulk reservoir characteristics, SRV. And these are useful characteristics, but wouldn't it be nice to complement those? And this is, Dwayne alluded to the missing perspective, the high resolution characterization. And there's many examples of this. And in this webinar and the following one next week, folks are going to talk about a lot more of these value propositions, these specific value propositions of high resolution characterization that we couldn't get from just RTA alone. So that's really sort of setting the stage for the unique and exciting opportunity that we're in right now. Poor oil price aside, as a reservoir engineer, it's a pretty exciting opportunity. Again, your blunt instrument and your surgeon's scalpel. So just quickly, I'm going to talk about probably one of the more important value propositions for shutting in a well. And this will be, John's going to talk about this in the next webinar as well. And this is the idea of, when we have a well that's on production, of course, we're going to see production decline over time. If there was nothing to cause that decline, you just have the production going flat. If there was infinite amount of energy and the well had constant productivity, you'd never see it decline. So what we see is some component of that is due to reservoir depletion, and some component of that decline is due to productivity loss. In the RTA world, we really have a hard time distinguishing between these two. Sometimes we can, and usually where we can do it is where we have availability of shut-ins. But if we just have this sort of smooth decline behavior, these things happen at the same scale, and it's notoriously difficult to determine the difference between depletion and productivity loss. So I actually have a full-length paper. I didn't have time to put the reference on there, but we can get that to anybody that wants further reading on that. So we did a whole bunch of case studies where we discussed that issue of productivity loss in wells. So the primary value proposition for an extended inline pressure buildup is this, right? We have our rate and our flowing pressure. RTA is going to estimate, and that's why I showed it as a dotted line, average reservoir pressure. This is inferred by the RTA, but of course is not measured directly. That's the big thing about RTA. If we were to actually shut in that well and see, and I've seen this happen time and time again when we have access to shut-in data, which in some cases we do, in many cases you see that pressure build up to something different than what you predicted the depletion pressure to be. In many cases it's higher, and that's our sort of our dead giveaway that we have a productivity loss in that well. So that productivity loss can actually be measured and retrofitted back into the actual production data, and it gives us a calibration point that we otherwise wouldn't have had. And imagine scaling this to a vast number of wells that are going to be shut in now. We're going to get a lot more information that we wouldn't normally have access to. Some of the causes of this productivity loss, you guys are familiar with these already. There's all kinds of things, especially in a tight, hydraulically fractured play. Low matrix permeability with hydraulic fractures, especially with high pore pressure to begin with. You have lots of sources of productivity loss that can happen with time, as a slow accumulation with time, or event-driven productivity loss events such as frac hits. These are all things that we're familiar with, and with a combination of a flow and shut-in with buildup, we can measure these things with really good precision. Here's an example. So the RTA component is shaded here, and that's what our RTA looks like. We plot it on a type curve or a specialized plot. We can get, sort of do a data match there, and that allows us to characterize that total hydrocarbon system. That's our buildup. You've seen a couple of these already. Dylan's going to talk more about this in detail, how an inline flow and buildup would look like, but we can get more detailed characterization on the buildup. A couple more comments before I close off, because I think this is critical. When you are collecting bottom hole gauge data, if you're going to run temporary bottom hole gauges, this is the most important or most critical spot to pay attention to, the point right where you're shutting in. It doesn't do any good to start collecting data after you've shut in the well. What you need to do is run those gauges before the well is shut in, ideally as far in advance of the shut in as you can. Unfortunately, the ship has sailed for some wells already, but on other wells, maybe you're planning shut-ins, run those gauges before you shut in the well. Why do you need to do that? Well, your flowing pressures that you're monitoring at the wellhead are not necessarily going to line up with those shut-in or with those bottom hole recorded pressures. So we want to make sure that we can do those corrections. And now we'll have a much more reliable analysis that comes out of it. So some final thoughts. 2020, we'll see the resurrection of PTA. We're going to take the dust off that tool, the build-up tool. Inline build-ups can complement and enrich previous RTA work. We're going to see a lot of that going on. And of course, there's some other tests that can add value in a shut-in environment as well. So that's it for me in terms of the formal part of the presentation. Happy to take any questions now.
This comes from Angie Fenton. Hi, Angie. How important is it to have a constant production rate data set prior to your shut-in?
Yeah, that's a good question. It's not critical. You're going to get a better quality buildup response if you're able to maintain a constant production rate for as long as possible. When we used to do conventional flow and buildup tests, we used to say, now mind you, this is higher permeability environment. We used to say you want to have at least a 24-hour period where you've got constant production rate. And we sometimes would do multi-rate tests to try to measure skin and things like that. So I'm going to say in a low perm environment, you want to try and at least have that. So if not more. Now, sometimes it's impossible to do that, like maintaining a constant rate on a low perm fractured well in a depleted reservoir might be impossible to do. What you really want to avoid are any last minute choke changes or disturbances, because that's going to mess with your buildup data. So your buildup is really an extension of what happened immediately prior to the buildup. And you want that data to be as clean as possible. So you want to design a test that's, if you have to deal with a slowly declining rate, that's okay too, because we can use like a Horner time or material balance time to sort of get the equivalent constant rate solution for that. So I think that's going to be okay. The trick is just avoiding any severe disturbances at the last minute.
Okay, we have another question from Rick Fear. And this is something that's come up in my reporting on this topic a lot. How big of an issue is crossflow in the lateral when trying to conduct a buildup test for PTA? And this applies obviously to extended reach horizontal wells.
So Rick has to come in here and ask me like A PhD level question. Thanks, Rick. Thanks for that. Yeah, that's a really good one. Rick and I used to work at FICAT together years ago. He can probably answer that question better than I can. It's not something I've seen, very often in a practical sense. Crossflow is, one of those things that's notoriously difficult to identify and measure in a test. And it's one of those things that experts argue about all the time. I've heard some experts say you won't see any crossflow in a buildup, which I think is what Rick was asking about, as opposed to a drawdown. I think there's different things going on there. So I'm going to give you the politician's answer here, which is just dance around the question and not answer it.
I think this one's a good one. We may have time for one more question here. And I just lost it. Here it is. This comes from Daniel Wong. What are the pros and cons of different type curves? So the Blasingame, Argowal, Gardner, MPI, etc. Which flavor would you tell people to pick?
Yeah, I think it's one of those things where you can use whichever ones kind of strike your fancy. They're to be honest with you, and I say this more, in hindsight's 2020. At the time that we were building a lot of this stuff into the Harmony and RTA, we were like, wow, this does this and this does this. Now that I look back on it, it's like, really, they're all, if you use a well-defined approach and repeatable workflow, they're probably all going to give you consistent answers. They're all based on that same constant rate drawdown equation. They all have the same physics. Some of them have, focus on different parts of the data. For example, transient style type curves focus more on transient data. So that's good for tight gas and tight oil applications. Blasingame versus Agrawal. These are tools that were used more in the conventional and tight gas environment, not so much in, multi-fract horizontal wells. We've transitioned into different tools there. So, the different types of type curve tools, they're all, they all have their use. They're just like any other tool in the toolbox. You just need to make sure you're using it with the right kind of data that you're trying to analyze.
Okay, well, I think that that makes for a good segue into our last speaker. And just to remind everybody, I see there's a lot of great questions coming in, and I think we're going to get to a lot of these, if not all of these, with the Q&A session that's coming up right at the end. With that, I'm going to go ahead and introduce Dylan Lahi. Flow and build-up test will be his topic. Dylan's a co-founder and CFO of Saga Wisdom and a very experienced engineer in his own right. And I'll let him go ahead and flex his muscles here. Dylan?
So I've got this nerdy background. As you can see, I'm going to nerd out for a little bit on some examples. This actually was provided to me courtesy of IHS Markit. You can get a link from them. Hopefully we can provide that later to download this. And this was actually developed at FICAT Associates, where I used to work a little while ago. And it basically provides a series of kind of almost like a cheat sheet of curves that you can look at to match with what you're seeing in your well test data and try to determine what's going on in your well. So definitely a great resource. I'm going to reference this in my presentation here. All right, so let's get into some examples here. The first example I'm going to show you is an example of a near well productivity impairment. So this is a multi-frac gas condensate well, kind of on the microdarcy level, maybe 100 nanodarcy level. And it was shut in post flowback for about a month. So you can imagine just after flowback, the fracs are cleaning up. There's still a lot of dynamics going on, and there may be some impairment to flow near well or near fractures during that time. So this is the test. I'm going to address a couple of the questions that were thrown at Dave here. So you can see gas rates and oil rates, and then in dark blue is the sand face pressure. So this is the gauge pressure. You can see the gauge was run before the well was shut in. As Dave said, that's very critical to obtain information, especially for if you're assessing damage. I would say all is not lost if you run gauges later on in the well's life, but you're going to be missing those near wellbore effects. The other thing I heard about is it critical to maintain a constant rate? You can see they tried to maintain a constant rate here during the last bit of the flow period, but there's a whole bunch of other production here, step changes in production going on, one big rate spike here at the start. So what I want to also address is that with modern tools, you'll find that they are able to accommodate for this using what's called superposition. So I'm not too concerned about varying rates. I've seen that quite a bit. But what is important is to get that clean shut-in data. So you can see on the left here, I'm showing the well test type curve plot for the drawdown. And then on the right, and maybe the screen's mirrored, I've been told my screen's mirrored here, is the derivative plot for the buildup. So notice the difference in the data quality we're getting. So in the drawdown, particularly the derivative, which is in red, is basically unanalyzable data. Whereas in the buildup plot on the right here, you can see this nice clean delta pressure response in blue, and then this nice clean derivative response in red. And note the character that we see in this derivative. So that character is hidden in that shut-in data. So we use the derivative to abstract that information and extract reservoir properties. So let's go right into an analysis here. And what I've done is I put a half slope line on the data where it starts to get to that half slope signature. And that denotes the dominant flow regime in fractured horizontal wells and vertical wells for that matter in tight rock. And that is flow, a linear flow towards the fractures. And one thing to note here, although that's expected, is that this flow regime doesn't happen until, or we don't see it until about 200 hours or almost 10 days into the test. And so what that's telling you is before that, there's some other dynamics that are influencing production and more dominant before we get to that linear flow period. So that's the first clue that something's going on. The second clue is this separation between the delta pressure and the derivative plot. And, you know, well test analysts will tell you that, you know, this typical large separation is indicative of a skin, which basically all that means is that there's some extra pressure drop in the system that is near wellbore, and I would extend that in unconventionals to possibly near fracture. Okay, so we've got some extra impairment to flow here. What would happen if we could remove that impairment to flow? So what I'm showing here, I've already modeled this data, and of course I had to use a big skin in order to match the data, confirming my observation, but I can use a model to say, okay, what happened if I remove that skin? And so what I'm showing in these solid lines here is the well test type curve for removing that skin. And you can see that I've got minimal skin here and minimal separation. And now that linear flow period happens after 2 hours. So what does that mean? That means that this would be a higher rate situation. So what I'm saying here is if you can do something to remove that damage, for example, this could be scaling. If you can do something, detect it, remove it, you have the chance to actually get an increase in production after shut-in rather than a decrease in production. And in this example, it's about a 15% incremental 1-year production. So this is this signature that I'm showing in the model. I want to reiterate that it's something that I see quite often and other people will see quite often in build-up tests, and it's confirmation that your well's doing fine. So this is a real thing. You can get wells that look like this. Okay, the second example I'm going to show is a little more interesting. It is semi-conventional, and I'm bringing it up because it's an extremely long shut-in. This is a Montney well. It's a hydraulically fractured vertical well, and it's drilled within a layered system with a very high perm coquina as part of the target. Now, this was provided to me courtesy of Halo Exploration, so thanks to Halo for providing this. And this was kind of the appraisal well, and so they shut in the well for a period of time while they got everything together to bring in infrastructure and drill some horizontals. So here's the test. You can see it's a pretty good well. It comes on at 600 barrels per day. And then they shut in the well. They actually reran recorders here. And that well continues to, they continue to monitor data for 7 months. And you can see how the pressure here is almost flat, indicating we've reached reservoir pressure again at the wellbore. So a good indication of reservoir pressure will come out of this test. Looking at the buildup plot here in the derivative, we see something very interesting. And if you look at that chart that I previously put up in my, or I guess you can see it in my background flipped, this is indicative of 2 systems. So, and basically what's happening is you have a higher productivity or a higher permeability storage system that exhibits in the first part of the test, and then a lower permeability system in the later part of the test. We're also seeing a curve down the derivative here, which is indicative of you seeing some reservoir boundaries, at least one boundary, and that gives you an idea of the size of that second system. So what do we get out of this? Well, first of all, I mentioned reservoir pressure. I almost never use the term accurate in anything subsurface, but I'm confident that you've got a pretty accurate number for reservoir pressure in this case. What we also get is some descriptive parameters of our system. We've got this higher perm streak here, around 100 millidarcy permeability. Then we have this 1 millidarcy permeability zone outside of that. And also what was interesting about this is in order to match the data, the well had to be placed sort of to the edge of this high perm layer. And we went back to geology and some of the suspicions on the geologists and the work that they've done really was commensurate with this. And another thing is we get some idea of how much, how big these systems are in terms of hydrocarbon in place. And if you're confident in your petrophysics, this also translates into a drainage area for that well and a bounding of that system, which can give you some indication on what is, you know, well spacing, where you're going to drill your next well, for example. I should say that this doesn't mean that this is a complete size of the system. It could completely keep draining another system that's perhaps lower perm, but we can see quite a bit in this test. So that's going to really help with reservoir characterization. Just to show that I'm not making things up here, this is a model match in IHS well test software, and you can see I use that system to model the data, and it does a pretty good match. So those are just a couple examples to get you thinking about what you could learn in a well test. They are not exhaustive, but what we've shown here is, number one, you can detect impairments to flow near well or near fractures. You can get a determination of reservoir pressure, obviously more accurate as you increase the time of the test and with higher permeability. You can get permeability of the system, and we've shown how you can see some of the complexities of the reservoir, particular in this case, a multi-layered system, you know, similar to what you might see maybe in the Bone Springs, for example. And you can get an idea of the size of these systems that can help with your future drilling plans, future completion plans. So again, thank you to Halo Exploration for showing us that fantastic well. And again, there's some resources at the bottom. We'll figure out how to get the links to you guys after this.
Dylan, I have a question for you that it was actually posed to Dave, but I think that you can answer it. Downhole data is superior, but can you talk about how to make the most of shut-in data for wells that lack downhole gauges? Even if the result will not be as good as downhole data, what insights can be had?
Yeah, so I've looked at lots of wells that were that have not had a bottom hole gauge run in them, and certainly we always want bottom hole gauges as PTA people, but yeah, you can still learn a lot from the surface pressure if you have that opportunity. Particularly here, I've looked at ones in Canada where they have facility turnarounds and you get that free buildup data, and I think that's what we're seeing here is we get free buildup data, like Dwayne was saying. infinite ROI. So some of the things that you have to be careful of is calculating bottom hole pressure. And quite frankly, you have a lot of the same problems in RTA, and we do it anyways. But if the well has liquids, if you can go in and shoot a liquid level, that'll give you a better indication. That would be sort of my first recommendation. You can make some assumptions on liquid levels and where they are depending on the well, which can help you. And I think another key thing to do is differentiate between what you can get qualitatively and quantitatively. So even if you can't determine what the exact bottom hole pressure is at the wellbore, the signature of the buildup at the surface is still telling you something. There's reservoir information in there, particularly after a little bit of time where things have stabilized in the wellbore. So you're gonna see some of the far field effects in those sorts of situations.
You talked a little bit about how PTA can indicate whether there's damage. Can you quantify that damage, and can you determine the cause of it by looking at this data?
Yeah, so number one, you can quantify it and there's a number of ways to do that. I mean, the easiest way is to just call it a skin, which is a reservoir engineer's fudge factor, which is an extra pressure drop. I don't know what it is, but that is a quantitative number. So you can compare wells and you can see, and people will tell you what a good skin is and a bad skin is. Sorry, what was the second part of the question? Oh, you're on mute again.
Are you able to determine the cause of the damage?
Yeah, so with PTA exclusively, no, that's not going to tell you the cause, but we have plenty of other well data and reservoir information that can get you to that. So for example, let's say the reservoir has a history of scaling. Well, that's the first thing I would look at is this a scaling problem? And you can fix that, right? Is it a extremely overpressured reservoir where you might have actually damage to your fractures, right? That's another thing, a little bit harder to deal with. So I think in most cases I've seen there's at least one or two, you can narrow down to about one or two possible causes of the damage, and usually you have that information in-house.
Dylan, I'm going to ask you one more question, and I think we will open the Q&A session for everybody. So I'll throw this one at you, though, here last. In unconventional horizontal wells, folks sometimes do a toe defit in the child wells and then stimulate this in many stages. Given the current situation, if this well were shut in and PBU monitored, what can we expect the signature to tell in current parent-child placement scenarios?
Okay, so if I understand correctly, we've got a defit, and then we're also doing a buildup as well, and looking.
Well, it sounds like we're doing the defit, and then we go ahead and frack the well.
Yep.
And if this well were shut in and PBU was monitored, can we draw some correlations between the parent-child relationship? I think this relates to spacing.
Yeah, so I mean, there's a bunch of things you can do. First of all, if you had parents there that have been producing for a while and you had some idea of initial pressure, now you know from the buildup test, if it's not building up and extrapolating to something that's similar, then you know there's some depletion there. Well, that's interesting. And you might even, if that well was fracked in a different bench or something like that, then that might mean drainage into another bench. Implications obviously on well configuration, pad configuration. If we've seen plenty of well tests where you monitor shut-in data, another well's being fracked, and you see where you're getting frack hits. That's communication during the frack, which is different, of course, than production, but that tells you something about how the wells are talking to each other. I know Trevor's in the next webinar is going to talk a little bit about interference testing, and I think there's an opportunity there, whether you do an injection test or a drawdown test with interference, because that's telling you now, after the frack and after wells have been producing, how wells are talking to each other. And that's information we rarely get, at least concretely in reservoir descriptions, right? We rarely get an opportunity to say, okay, how are fractures connected post-frack, post-production? So, yeah.
Okay, thanks, Dylan. So now we kind of have a open period for the next 10, 15 minutes, I think. I know we're a little bit over, but this has been a really thoughtful discussion from everybody. And so for all the speakers, I'll let you guys raise your hand and jump on some of these questions that remain open from the audience. One of them that I liked, and this may not be applicable, but let's see. What can you tell me about the GOR behavior and the SRV evaluation and the other evaluation methods? Can your other analysis start to play a role here?
Yeah, maybe I'll chime in on that one. Yeah, if you're talking about, a buildup helping define those things, the way I would look at it is RTA, again, it's, think about the blunt instrument tool. RTA is a really nice tool for characterizing hydrocarbon pore volume. What we can't get from it are things like individual boundaries or shape factors, or as Dylan was talking about, individual impairments. We get more of a bulk property. So what I would say is a buildup is going to give you a different perspective. It's going to add some more detail to that knowledge. It might help, steer your modeling in a different direction. One of the issues we have with RTA is we get these bulk parameters, and then when we're trying to build a model to match the data, we have a lot of uncertainty. So we have to do probabilistic models. And I think what a buildup can do is it can narrow down that selection of probabilistic models because it gives you more data to constrain it. And that would be true of SRV and other bulk parameters that you might measure.
And I would add further, because it's more of a near wellbore investigation tool with high resolution and a better understanding of that early performance data signature, it can offer a deliverable that RTA can never provide or standardly doesn't provide, which is in a shut-in and a buildup, you can sometimes get bilinear flow observed in terms of flow regimes that are at least observable with the data set that you have. And then from that, reservoir engineers know that provides fracture conductivities, KFWs, which is really a great field test for measuring frac conductivity. We talk about doing this in the laboratory all the time. The people that manufacture these specialty proppant materials like Rainbow and Carbo and the others, and they try to say, look at what our conductivities do with our materials under different confining pressures or stress. Well, now we've got ourselves a buildup that can actually measure fracture conductivity in the field. And so we could then compare that to the laboratory results. And I don't understand why more people aren't doing that because we do often see bilinear flow and buildup data. So it's not, sometimes there's more to, more to the deliverable than what people recognize.
Let me ask a question to the operators here that just came in. In your experience, how can we eliminate or minimize H2S and CO2 corrosion during the shut-in? Is there anything you can do?
So yeah, I can start off, and then maybe Trevor can add if he's got any thoughts. But it really depends what the mechanism is that you're seeing the H2S and CO2 come in, and what you've been doing to treat it. So if you can do some proactive treatment to your wells before you shut them in and set things up to address corrosion and those things before you do it, and then highly monitor when you bring the wells back online. Are you seeing a step change in H2S that is less or higher that you need to change your treatment to kind of hold the integrity of your wells?
That's good, Nathan. I'm not on this, but the only other thing I may add is in a lot of cases where H2S is observed, making sure that you run a packer at the end of your tubing if tubing is in the hole. That way you're trying to confine the H2S and the exposure to, just your tubing. It can definitely minimize, if you do end up with any issues, what the remediation costs may be. I'm sure most people are aware of that, but just a note.
I have here one from Heather Christie Burns. To what extent is productivity loss due to relative permeability effects, i.e. gas versus oil ratios, typically wells gassing out over time? Do you find that shut-in times as a factor can alleviate the saturation issues? And how would you measure this? What data would you look for?
Yeah. So I can answer some of that. I'm thinking of a slightly different example than Heather's there, but for example, we've seen wells where post flowback buildups and then a buildup maybe a year later or two. And often what you see is a reduction in sort of that damage profile. And what I would attribute that to in a lot of those cases is you no longer have, for example, if it's gas, you no longer have water, frac water impeding the flow, right? That it's had time to either be produced or sucked further into the formation so that you now have a pathway for gas to flow. So I think people make the mistake sometimes early time that say, oh, this well is damaged. And whereas really it's just, you know, it's your frac water interfering with production, and that can change over time.
Does anybody else want to add to that?
The damage sometimes goes the other way. Sometimes, and a pressure buildup is a single point in time. And sometimes you'll take the same measurement multiple times, buildups over years, and you'll see the frac conductivity later in life diminish from test to test. And that, once it happens, that is an irreversible damage.
I think I would add, I think we're going to learn a lot. Like the question that Heather asked, I think largely doesn't have practical answers right now because we just haven't been in a situation, for example, where we have a highly fractured low permeability reservoir with multi-phase flow where we've been able to trace, you know, what we see as relative permeability issues during RTA and then shut it in and see what happens. And I think, you know, one of the things I would expect to happen is some level of fluid segregation occurring during the shut-in. Whether or not that's going to cause a measurable difference in skin in the shut-in, I mean, that would be an interesting thing for us to try and find out. That's one of the suspicions we have in these tight fractured production scenarios is that, you know, if you do have these fractures, sometimes you will get gas going to the top and causing some sort of gas storage system at the top of the fractures. So I think we're going to learn a lot, I guess, is the answer to the question.
I like this question a lot, and so it'd be interesting if the operators could take a stab at it. Dwayne, you as well. If a drawdown strategy has led to a change in productivity, say a recent choke increase, what are your thoughts on the damage being reversible? So you're monitoring, can you go in and change something based on what you're seeing?
Yeah, I'll go ahead and Trent and take a stab at it. So from my experience, what I've seen in multiple basins when that happens is usually I haven't been able to see anyone reverse it. So you've had some sort of collapse in the fracture network. I have seen times where you've had offset fractures hit wells and you get some restoration there and you get some production, but then usually it's short-lived.
That's been my experience as well. So nothing to add to Nathan's comments.
Yeah, I'd say the same thing. The damage is mechanical. It's a physical change to the system, and there's no way to repair it.
Well, that's great news, guys.
It's not universal, right? It's not every well that happens to.
Well, I really appreciate everybody joining in. We had over 350 people at the peak of this webinar, but we're going to end it here on time. And I'm going to hand it over to John Thompson, who's going to fill everybody in on next week's program.
Yeah, thank you, Trent. I want to remind everybody that we're doing the whole thing all over again next week with a different lineup of speakers and topics. There's many questions that are left outstanding. I can see in the chat rooms and in the Q&A. There's more questions that we can possibly address today. Hopefully you can ask those again next week. We can get to them. And of course, if they're in the Q&A, we will review them and we'll try to do our best to get back to you right away. I did also want to thank Angie Fenton and the Women in Hydraulic Fracturing who graciously helped us with the logistics, because this is the first time we've done a technical webinar coupled with LinkedIn and Zoom. So appreciate the help, Angie, there. I also wanted to quickly share my screen. So we're going to talk about operational considerations and restart criteria from Nathan. Dwayne will talk about the risk factors for productivity loss. I'll then be talking about assessing and quantifying pressure-dependent production. And Trevor is going to talk us through maybe one of the most important deliverables from the the great shale shut-in, as Trent called it in the SP-JPT article of his, interference testing to optimize development. So thank you very much for tuning in. I know a lot of you have also asked questions about the materials. Are the slide decks going to be made available? The short answer is yes. If you contact us, we'll try to assemble a bit of a master deck for you at the conclusion of the next webinar, and then we'll only have one big file to send out. So please, please wait until we get all the materials put together for that. And this webinar is recorded and will be hosted on the Saga Wisdom YouTube channel. If you type Saga Wisdom in YouTube, you'll find us quite quickly, and we will be hosting it there shortly. So thank you very much, everybody, for tuning in. Thank you, panelists. Thank you, attendees. I look forward to seeing most of you next week.
Thank you, everybody.